In project number 4, we're going to implement 3 things for the file system. First one is buffer cache, and then second one is make the files indexed and extensible, and implement the concept of subdirectories. The first one I'm going to explain is buffer cache. The idea of buffer cache is simple. We use the part of memory as the disk. This is an opposite concept of virtual memory and swap space. Let's say this is memory, and this is disk. Virtual memory is the concept of using a part of disk as a memory. It's something like this. So, say this part is mapped to memory, and this part is mapped to the disk, and this portion is called as swap space. This is virtual memory. In buffer cache, the concept is the opposite. Let's say this is buffer cache. We use part of the memory as the disk, something like this. Okay. So use part of the memory as a disk. That's the big concept of buffer cache. So part of the disk is mapped to the memory. That's buffer cache. So buffer cache is consecutive physical pages, and it is initialized when the system starts or when the file system is mounted. So if you unmount the file system and mount it again, all the contents in the buffer cache is reset. And so in current Pintos, there's no cache for the disk I/O. In reality, but however, in most operating systems have a buffer cache for the disk I/O. So we're gonna modify the file system so that we can cache the file blocks into the physical memory. In this project, you are going to allocate 64 file pages to be cached in the memory. Okay, this is how you are going to implement. Current Pintos accesses storage on every read-write request. So we have to change the user I/O to be performed through buffer cache, and we are going to add buffer cache layer here. This is before you implement the buffer cache, and this is after you implement the buffer cache. So this is a list of things to do. The first thing, of course, is define the data structure for buffer cache. And then you have to write a routine to allocate and initialize the buffer cache. And then you modify read and write routine so that they utilize buffer cache in reading and writing the data. And then, of course, you have to change the read-write routine so that if cache miss occurs, if you want to read the data blocks from the buffer cache, but if that block does not exist in the buffer cache, then you have to read it from the disk. Okay, so you have to implement a routine to handle cache miss. And there is another important routine you have to write. When you want to bring in the new block to the buffer cache, it is possible that buffer cache is already full, and you have to make a room for bringing in the new blocks. Then in that case, you have to evict one of the buffer cache entry and make it free. So this is you have to implement buffer cache replacement algorithm. And then you have to write a routine to write the dirty buffer cache. It is possible that after a block is read from the disk to the buffer cache, the application might have changed it, might have changed the contents of the buffer cache. In that case, you have to write the dirty page back to where it read from. So you have to write a routine that synchronizes dirty buffer cache to the disk. This is the list of things to do. It's very simple and it is very fun. All right, the first thing you have to do is define the data structure for the buffer cache. Define the data structure for the buffer cache. Okay, so buffer cache is a page in memory. Okay, and for use a page entry as a buffer cache, you have to define some kind of metadata structure that represent the contents in this page. So it has to contain a dirty flag. Dirty flag denotes whether a given contents has been changed since it was read from the disk. And it needs to have a flag indicating that whether the entry being used or not. And of course, there is we have to introduce the access flag. So it indicates whether the entry has been accessed recently or not. This access flag is used for the victim selection. When the operating system has to select one of the buffer cache entries to make a room for the new one, then there has to be a mechanism to distinguish hot blocks from the cold blocks. Hot blocks means the buffer cache entry that is being accessed actively, and cold buffer cache entry is the one that has not been used recently. So we have to have some type of mechanism to precisely identify the hotness of the block, and this is to let the operating system to select the data blocks that has not been used recently. It is important that when you have to kick out one of the buffer cache entries, you have to choose the buffer cache that has not been used recently, so that the performance is not affected by kicking out those entries. And also it has to have an on-disk location, and then of course it has to have a virtual address of the associated virtual cache entry. So we are going to allocate 64 pages for the buffer cache. So we need 64. Let's name the data structure as buffer head. Buffer head data structure. So we have to allocate 64 buffer head when the system starts. There are many data structures that can accommodate 64 data structures. We can use array, list, or hash table. Here we are using the table. So this is the table of 64 buffer heads, and each buffer head has a pointer to actually its location in the virtual memory. So this is diagram for the buffer cache. The act of reading, this is buffer cache. So act of reading a disk block from the disk to buffer cache is called caching. This is caching. And when some of the buffer cache is updated after it has been read from the disk, then you have to synchronize the contents of the buffer cache back to the place where it belongs. That is called flush. Okay, this is entire diagram for the buffer cache data structure, and this is the one you have to implement. And when an application program wants to read a certain block, then it has to search the buffer cache head table first to identify the location of the buffer cache. All right, so the next step is, I pretty much have explained everything for you to be able to define the data structure for the buffer head. So you should not have any difficulty in implementing the buffer head data structure. And the second issue is allocating and initializing the buffer cache. Of course, this has to be done at the system boot time and filesystem is mounted. So we are going to allocate, we need a space for 64 filesystem blocks. The block size is 512 byte, so we need 32 kilobytes to accommodate 64 file blocks. And of course, also we have to allocate memory for buffer heads, 64 buffer heads. So this is the size of buffer head times 64. This is the amount of memory you have to allocate for defining 64 buffer head entries. And this is done when the file system initialization time. So you have to add code here. That's pretty much easy. Okay. That's easy. Okay, so now let me explain the read and write in current Pintos. This is the function file read, and it calls a function called inode _read _at. Okay. Read, of course, the read system core takes two parameters. Of course, first one is file descriptor and the amount of data blocks to read. And then the operating system reads a certain amount of data blocks from the disk to the memory. Okay, so in current Pintos, this is how the read is implemented. There is a variable called size. Okay, every time it reads from the disk, it reads 512 byte. So it iterates this loop, reads and reads and reads until it reads amount of data that has been specified as a parameter to the file _read operation. So each time the size decreases by 512 byte. So eventually the size becomes 0 or negative. Okay, so read the full sector and then block read from the disk and compute the remaining read size. If the size of the read is still greater than 0, then it reads the full sector again. But it is possible that if you want to read, like, for example, 1500 byte, okay, then it reads 512 byte first, and then it reads 512 bytes again, 512 byte, sorry, then it sums up to 1024 byte. Okay, so the remaining part, 476 byte, needs to be read from the disk, but it is not a single block, right? It is not a single block, so you should not call a block read from the disk. And then so you allocate a bounce buffer and then perform partial read. The partial read means even though you read entire block from the disk, which is 512 byte, the application has asked you to read only 476 bytes from the disk. So read 5 kilobyte to the bounce buffer. And then copy only 476 bytes from the bounce buffer to the buffer designated by the read. This is 476 byte. So this is how you perform partial read. Okay, so now you have to implement this part. Of course, the entire diagram looks a lot more complicated, but don't be afraid, it is easy and you should be able to do it very quickly. So after calling the function inode _read _at, okay, instead of reading directly from the disk, you read the buffer cache. So you perform read in the buffer cache. First thing you have to do is find the buffer head. If it does exist, then read data from the buffer cache to the buffer and then update the buffer head. Here, what is updated is probably the access bit, access flag, denoting that this buffer cache has just been accessed. Okay, that's lucky part of the story, but life does not go always as easy as you want. Sorry, oops. Okay, so the first issue is what if the entry does not exist? Then you have to read the disk block from the disk to the buffer cache and perform the read again. Okay. So in that case, if the entry does not exist, then you have to bring in the disk block from the disk to the buffer cache. If the cache is not full, then that's better. Then you can just read the blocks from the disk to the buffer cache and read it again. So select empty entry from the buffer head, bring in the disk blocks, and then perform read. That's good. But the worst part is the case when the buffer cache is entirely full. Okay. Then if the cache is full, then it select victim entry. It has to select the victim to kick out and to make a room for bringing the new one, bringing the disk blocks. So select the victim entry, and if the victim entry has been modified since it has been brought into the memory from the disk, then we say it's dirty. Then we have to save it to the disk. We have to flush victim entry to the disk. And after flushing the disk, flushing the buffer cache entry to the disk, it has to release the victim entry and make it free. Okay. If the victim page is not the victim entry is not dirty, then it does not have to perform flush. It goes directly to releasing the victim entry. And then again, because now the free block is available in the buffer cache entry, operating system can perform read from the disk to the memory. Okay, so we have to modify the disk read to buffer cache read. The function we have to change is inode read at. Okay, so we have to modify the block read. So when reading a file, we modify the read to read the data from the buffer cache, not from the disk. Okay, so you have to modify this part right here. So this is the loop. Okay. the write has to be changed in similar fashion. So write is the same. It iterates in the while loop. If you want to write n disk n byte, then each time it iterates, Pintos operating system writes one block at a time. So each time it performs write, it decreases the size by 5 terabyte. Okay, and then calculate the remaining write size. Do it again and do it again and do it again. If the size is becomes 0, okay, then the write is done. So it releases the bounce buffer. But if the in case the remaining amount of data to write is less than a sector, okay, this is important and tricky part. We call it a partial write. Actually, partial write takes more time than a blind write. We call it a blind write. The blind write means they write full sector, so you don't have to read the disk block from the disk. But in partial, when you write entire sector, you can just write it to the disk. But if you write only part of, if you want to write full blocks, then just read it to the disk, write it to the disk, sorry. If you want to write the full block, then write it to the disk. But if you want to write part of the blocks, then what you have to do is you have to first read the contents from the disk to memory, from the disk to memory, then fill the memory part with the data blocks you want to write, then write it to the disk. So partial write is more expensive. So allocate the bounce buffer. You have to read the data blocks from the disk to the bounce buffer, and then perform partial write to the bounce buffer, and then write the bounce buffer to the disk. So partial write is more expensive. Writing with buffer cache is similar. So you have to write in the buffer cache. So find the buffer head if those blocks already exist in the buffer cache. If they exist, then you're lucky. Then update the buffer cache, and you're done. However, if entry does not exist, then you have to write that to the buffer cache. And then in that case, if the cache is not full, you're lucky. You select the empty, you find the empty buffer head, and then write the block to the disk, not to the disk, to the buffer cache, and returns. Okay. There is interesting part. Block read data from to the disk to the buffer cache here. This part. Read here, block read here is required only for the partial write. If you perform full block write, or if you perform blind write, you do not have to read the disk block from the buffer cache. Okay, if the cache is full, then you have to select the victim entry, and if it's dirty, then you have to flush the victim entry to the disk. This is the same as before, and then release the disk block. And if it's dirty, if not dirty, then release the victim entry from the buffer head. So in modifying the write, you have to modify disk write to write to the buffer cache. Write to the buffer cache. Okay. When writing a file, modify it to write the data buffer cache rather than to the disk. This is what you're supposed to do, and you are supposed to modify this part. Block write. Okay, so that's gonna be easy. So you're done. Good. All right. And one of the important things that remains you have to do is synchronize the dirty buffer cache entry. When you releases a buffer cache entry to accommodate a newly incoming disk block, you have to check whether the existing buffer cache contents is dirty or not. If the existing buffer cache entry is dirty, then you have to write it to the disk. We call it a synchronized. We call it a synchronization activity. Synchronize. So write dirty buffer cache entries. This happens when the buffer cache entry is evicted first, or if the file system is unmounted. Shutdown means unmounted. So there's a function called filesystem. Then you have to write a code here. Okay, that's going to be easy. So you should be able to do that. Or there is another situation you want to write the dirty buffer cache entry to the disk is periodically. So for example, in 5 seconds. 5 seconds interval. And in this case, you use time interrupt. Okay, so let me explain the details of read-write in Pintos. Reading a file is performed by file_read function. It contains 3 parameters. This is the pointer to the file object, and this is the pointer to the memory area which you want to read the data blocks into, and the amount of data blocks you want to read. This is size. Data structure struct file contains a pointer to the in-core or in-memory inode. Okay, and in-memory inode, Pintos maintains a linked list of inode that has been opened by the operating system. So inode list here, there's linked list here, and then each inode takes this form, and in memory inode it contains the struct inode, and inode on the disk. It contains start address and size of the file. So looking at inode disk, you should be able to find the location of the data blocks. Okay. The second one is write in current is Pintos. So let me go back. So it performs, if it performs write, yeah, this is the data blocks we have covered in the previous slide. So let me skip this slide. And then file write, we get 3 parameters. First parameter is file data structure and buffer and the size. Okay, and in file write, it calls the function inode write at, and it gets 3 parameters. First parameter is inode. Second parameter is the address of the buffer, and then this is the fourth parameter is size, and the fourth parameter is the current offset. Okay, so it passes the position from which you have to write the file to. You have to write the data blocks to, and right after writing some contents, you have to update the file position. And then you return the amount of data that has been written to the file. Okay, this is the details of the important function inode write add. Okay, it takes 4 parameters: inode, buffer, and size, and offset. So here, this is file, and this is offset. And in inode write add, you write size amount of data, and this is buffer. So you write, this is size. So you write this here. This is how inode write add works. Let's look at the details of the write function. Let's see that this is the amount of, this is a file, and you want to write from this position to this amount. Okay, and let's say this is 3 and 4 blocks. Let's say this is block 1, block 2, block 3, block 4, and block 5, but in block 5 you only write half of the block. Okay, this is file. This is beginning of the file. This is offset. This is start address of the file. Then when you write a file, the first thing you have to do is you have to change the offset to the actual location on the disk. Okay, so this is the function which translates the offset into the real sector address. Okay, and then you have to check whether the location you want to write the data block is aligned with the sector address. So you have to make sure that in writing to the disk, all the disk blocks should start with the starting of the sector address. So if the sector offset is 0 and the size of the chunk you want to write is the sector size, then you're happy, and then you can perform block write. Okay, so let's assume that you want to write the data blocks, but data block starts with the sector address, and then you should perform the full block write repeatedly until the size is greater than 0. But at some point, if the chunk size is less than block size, then you have to perform the partial write. When you perform partial write, which means that you have to, when you are writing part of the block, you need a bounce buffer, and you first have to read the data blocks from the disk to the bounce buffer. So you have to read the disk block from the disk to the memory, and then you merge the contents of the bounce buffer with the blocks, fraction of the blocks you want to write. So there's disk, and then you want to write part of the block. This is the contents you want to write blocks. And then you first have, this is bounce buffer, and then this is the block you want to write. Okay, then you read the data blocks from the disk to the bounce buffer, and then copy this portion to the bounce buffer, updating part of the contents in the bounce buffer. This is first step, and this is second step, and writing the entire contents to the bounce buffer. Writing the contents of the bounce buffer to the disk. This is how you update the disk block. That's easy, huh? So you're done. Again, we are happy. We are happy hackers. Happy hackers. Happy happy hackers. Good. Well, let me put some more hairs. All right, so this is the function called bytes to sector. It gets the inode and it gets the position. And then it returns the sector address of the given position. So this is very simple. Inode has a start address of the file. Okay, and then we have a position. So if the position is here, and then you divide it by the sector size. Okay. So position here is a position within a file. Of course, the position is byte. Okay. So we divide it by the sector. It means that how many sectors does it apart from the beginning of the file, and then you add it to the start sector number of the file, and then you will get the sector address of the blocks you want to write. That's easy. Okay, so next we're gonna explain the read. This is the read of the current Pintos. It reads from the disk, and if it's partial read, then allocates bounce buffer and read part of that. Okay, so this is same code. This is the code for the file on the var read. It gets 3 parameters. First one is pointer to the file. This is pointer to the memory chunk. And this memory chunk is the place where the operating system reads the data blocks from the disk to this buffer. And then the amount of data blocks you want to read. So this is size. So it contains 3 parameters: file, buffer, and size. Okay, so this is file. Okay, and then it contains pointer to the inode data structure. After reading a file, the file position is updated. This is the last slide of the explanation on the buffer cache. The function is inode and the bar read and the bar at. It reads a given file. So it takes 4 parameters: inode, buffer, size, and offset. So the inode represents the file you want to read, and the buffer is the start of the memory address you want to read the file to. And this is amount of data blocks you want to read. And this is the position of the file you will start reading. So similar to the inode write, it iterates, and for each iteration it reads a block, and each time it performs read, it performs the read on the block device, and then each time you provide a sector index. So this is the sector you want to read. So after reading the full block, you will perform the partial read at the end of inode read at. So this is the end of the explanation, and I hope you enjoy the project. Good luck. We are happy hackers.